In Section 3 of Chapter 7, we're going to discuss the formal methodology for drawing valence electrons around atoms. Those could either be around neutral atoms or ions, so both cations and anions, or they could be in simple molecules that are covalently bonded together. We're going to call these structures that we draw Lewis dot structures. Lewis dot structures are often just called electron dot structures today. Lewis was the first scientist to actually develop this methodology. His methodology said that we could represent the atom's valence electrons by simple dots around the element name or its element acronym itself. So these dots, and based on where they're actually placed around that two-letter acronym, will represent the valence electrons distribution in a molecule or in an atom. So covalent compounds, they typically follow the octet rule. They want to have an octet of electrons in their outermost valence shell. If we look at some examples of that, we have neon, which has 8, argon, krypton, xenon, and radon. Those are the noble elements, and they all have 8 electrons in their outermost valence shell. Helium is also a noble element, and it only has 2 electrons because its outermost valence shell is just the 2s shell. Rather than drawing all of these dots around that elemental element here, Lewis just said, let's just draw the valence electrons and let's place them symmetrically in pairs around the 2-letter acronym or the 1-letter acronym for the element. So helium has 2 electrons, neon 8, argon 8, krypton 8, xenon 8, and radon 8. We consider these the Lewis dot structures or the electron dot structures for the 6 noble elements. Let's draw the Lewis dot structures for all the elements in period 2 of the periodic table, so the ones here that are shown in red. So I'm going to take the elemental symbol, which is either a 1 or 2-letter acronym, and then I'm going to place the valence electrons around them. So lithium has 1 valence electrons, beryllium has 2, boron 3, carbon 4, nitrogen 5, oxygen 6, fluorine 7, and my neon, my noble element, has 8. Notice in some cases we have the electrons paired up, and in other cases we have them sort of as single electrons. So we can represent them as paired electrons, or we can represent them as unpaired electrons. Let's draw the Lewis dot structure of some atoms and then combine them to actually form a covalently bonded molecule. So if I start off with hydrogen, I have 2 hydrogen atoms. Each has 1 valence electrons, as shown here in this electron dot structure. They come together to form a covalently bond molecule. Now I show the electrons as an electron pair. We could also represent that electron pair as just a line between those two. It means the same thing, and we often draw it as just a simple line because it's easier. Let's use the electron dot methodology to show how we can take atomic fluorine, 2 atoms of fluorine, react them together to form molecular fluorine. So if I look at each fluorine atom, they contain 7 valence electrons, one of which I've shown here in this electron dot structure as being unpaired. These 2 red ones are the ones that are going to come together to form a bonding pair or a shared pair of electrons. I could also draw that as a line here. A line between 2 fluorines represent a bonding pair of electrons. Let's use the Lewis dot methodology to actually show the reaction between oxygen and hydrogen to form water. Oxygen has 6 valence electrons. In the dot structure, I've paired up 2 of them and paired up a second pair here, and then I've left these 2 electrons unpaired. These are the electrons that are going to form a covalent bond with my unpaired electron and my 2 hydrogen atoms to form water. So these are my bonding pairs of electrons, and these two are still my unpaired, or sometimes called a lone pair of electrons. Drawing it with lines instead of dots, here is the molecular formula for water. Here is a more complicated molecule. This is ethane again. In this case, I'm going to take my 6 hydrogen atoms, which have 1 unpaired electron, and 2 carbon atoms, which have 4 unpaired electrons. Start sharing electrons between them to form bonding pairs, or I could have drawn this with this lines. So this is the molecular structure of ethane. When forming molecules, you can often share more than just 1 pair of electrons. And when you share more than 1 pair of electrons, we actually form multiple bonds here. So let's look at oxygen as an example, and let's use the electron dot structure to actually show this. So here I have oxygen atom with 6 valence electrons. I have a second oxygen atom with 6 valence electrons. If I share 2 electrons, I now have 7 valence electrons around this oxygen atom and 7 valence electrons around this oxygen atom. If I share one more pair of this unpaired, I can actually now see that I have 2 single bonds or 2 covalent bonds between the oxygen, but I now have 8 valence electrons around each oxygen, because I could represent those 2 electrons as 4 shared electrons here, 8 around this oxygen and 8 around this oxygen. We have 2 electron pairs formed, and we're going to call this a double bond now. Some atoms, like nitrogen, can actually share 3 pairs of electrons to form what is known as a triple bond. If we look at the Lewis dot structure for atomic nitrogen, I've drawn this as if I have 3 unpaired electrons and 1 paired electron on this nitrogen, and 3 unpaired and 1 paired on this nitrogen. If I form a triple bond, I share 6 electrons now between the nitrogens. You can see I have 8 around this nitrogen and I have 8 around this nitrogen. We represent this as a triple bond now. When we start moving to more complicated molecules, Lewis developed a methodology for actually creating a Lewis dot structure for covalent molecules, and it's a 5-step process. Let's now look at that process. So the first step is actually to count the total number of valence electrons from each atom that is coming together to make a molecule. There are also some caveats here. I add 1 additional electron if I have an anion coming together, and I subtract 1 electron from that if I have a positive charge for a cation. As an example, let's draw the electron dot structure for carbon dioxide, CO2. So let's do step 1 here. Let's count the valence electrons for each of the atoms coming together. I have 4 valence electrons for carbon, and I have 6 valence electrons for each oxygen, for a total of 12. And I easily determine that because I came over here. Here's carbon. That's in group 4A. That has 4 valence electrons. I look for oxygen. That's in group 6A. It has 6 valence electrons, but I have 2 oxygens. I add those all up together. 1 times 4 plus 6 times 2, I get 16 total valence electrons that are going to count for all of my bonding pairs and any non-bonding pairs. Step 2 is actually to put the atoms down and actually connect them with lines. These lines will represent a bonding pair of electrons. There are many different ways you could actually put them together, but the most effective way is to actually put the least electronegative atom in the center and then put the other atoms outside of that. So in this case, I put carbon in the center and I've connected oxygen to them. We still need to keep track of all of our electrons. Together, all of these atoms brought in 16 valence electrons. I have now used 4 of them to actually create a bonding between the carbon and oxygen. So I still have to account for 12 more electrons that I need to place around these atoms here. The third step is to take any of my remaining electrons that have not already been used to form a bond and assign them to the terminal atoms to actually fulfill their octet. So in this case, I take oxygen, I add 6 electrons to form 8 around oxygen, including the pair that's bonding between oxygen and carbon, and I add 6 to this oxygen to form 8, including this pair here between my carbon and oxygen to fulfill its octet. When I do that, I started off with 16 valence electrons coming from oxygen, carbon, and hydrogen. I used 4 of those to form a bond between the carbon and oxygen, and I just added 12 electrons, 6 to each oxygen, to give them octet. That gives me 0 electrons remaining. Step 4 is to assign electrons to the central atom. Remember though that I have already used all my electrons. I already assigned any of the non-bonding electrons to oxygen. So for this example, this step is not required, but we will use it for other atoms. So all my electrons are already used. Step 5 is the use of multiple bonds to create octets. So if I have no unassigned electrons that remain after step 3, but my central atom does not yet have an octet, I want to use 1 or more of my lone pairs of electrons from my neighboring atoms to form multiple bonds, either double or triple bonds. So in the molecule that we're looking at, CO2, carbon only has 4 electrons around it right now. I need 4 more, so I'm going to use 2 electrons from oxygen to form a double bond, and I'm going to use 2 electrons from this oxygen to form a double bond, to form 2 double bonds now. So if I look at this oxygen, I have 8 electrons around it. I have 8 electrons around my carbon. I have 8 electrons around my oxygen. This is a good representation of what the electronic structure and the bonding nature of CO2 should be. Let's draw the electron dot structure for some more molecules now. And let's start off in this example, draw the electron bonding structure for CF4. Step 1. Carbon brings in 4 valence electrons. Each of my fluorines, 4 of them, brings in 7 for a total of 32 valence electrons. I arrange my atoms so that I put the least electronegative in the center, and I put fluorine out here on the outside. Each of these represents bonding electrons. So I started with 32. I'm now going to subtract 8 from that. I then, to fulfill the octet for fluorine, I put the remaining electrons that I have around each fluorine for a total of 4 times 6, or 24. That leaves me with 0 electrons. Notice that I don't have any electrons left, so I can't do step 4, and my octets are all complete, so I don't need a step 5 in this case. This would be the final electron dot structure for CF4. Let's do the electron dot structure for CH2O. Carbon brings in 4 valence electrons. Each hydrogen brings in 2. My oxygen brings in 6 for a total of 12 valence electrons. I arrange them with my least electronegative in the center, using up 6 electrons to form single bonds between my carbon and hydrogens and my carbon and oxygen. So that's 6 bonding electrons. I then take my remaining electrons and I've put electrons around oxygen to fulfill its octet, so I use 6 of them there. I don't have to do that for hydrogen, right? Because those already contain 2 valence electrons around them, so that fulfills its outermost shell. I do the math here. I have 0 electrons left over, so I cannot do step 4 where I put any remaining electrons around the central atom. Step 5, I'm going to use some of those electrons around oxygen to form a double bond with carbon, and I end up with this final electron dot structure for CH2O. This is commonly known as formaldehyde. Let's draw the electron dot structure for N2. I have 2 nitrogens. Each of them brings 5 valence electrons for a total of 10 valence electrons. Since the atoms are identical, I just connect them with one bond, which is 2 electrons. That gives me 8 electrons remaining. So I put those around nitrogen here, 1, 2, 3, 4, 5, 6, 7, 8. Notice I distributed those evenly. Again, I don't have any electrons left, so I cannot do step 4. And in step 5, I'm going to use some of those electrons that are isolated on each of the nitrogens to form 2 new bonds or form a triple bond. Each nitrogen now has 8 electrons around it to fulfill its octet, a valid Lewis dot structure of N2. Let's draw the electronic dot structure of the molecule COF2. Carbon brings in 4 electrons. Oxygen brings in 6. Each of my fluorines brings in 7 for a total of 24 valence electrons. I arrange my atoms to put carbon in the middle since it's the least electronegative. I then form 3 bonding pairs, so that's 6 bonding pairs of electrons. I then start putting electrons on each of the outside atoms, 6 on each of them, so 3 times 6 equals 18. I've used up all 24 of my valence electrons now, so I can't do step 4. However, carbon does not have 8 valence electrons around it, so I'm going to use those electrons from one of my outside atoms here to form a double bond. And as we're going to see, I'd like to use oxygen's electrons. That is the closest in electronegativity to carbon, so I form a double bond between carbon and oxygen. And this is the final valid Lewis structure for COF2. If we kept on drawing Lewis dot structures for molecules made out of hydrogen, and these atoms highlighted in red here, we tend to see that there's sort of a common theme that's arising here. Hydrogen likes to have 1 bond to it. Carbon likes to have 4 bonds to it. Nitrogen likes to have 3, and oxygen likes to have 2, and all of the halogens like to have 3. And we can sort of see that if we were to draw the Lewis dot structures for the atoms. Hydrogen, it has 1 unpaired electron. It wants to form 1 electron paired it up to form 1 bond. Carbon, we draw as 4 unpaired electrons. It wants to form 4 new bonds. Nitrogen, we draw with 1 paired electron and 3 unpaired. It wants to form 3 bonds. Oxygen, we draw the Lewis structure as 2 paired sets and 2 unpaired. It wants to form 2 bonds. Fluorine, chlorine, bromine, and iodine, we draw as 3 sets of paired and 1 set of unpaired. It wants to form 1 bond, 1 paired up to form 1 covalent bond. By knowing the number of bonds that each of these elements likes to form, we could use that methodology to actually create molecular structures very quickly. For example, in ethane, I know carbon likes to have 4 bonds to it, hydrogen likes to have 2. So, and I sort of put that together, the only structure I can draw where carbon has 4 bonds and hydrogen has 2 is this molecular structure. Hydrogen cyanide, I know that hydrogen likes to have 1 bond, carbon wants to have 4, nitrogen likes to have 3. The only structure I can draw in this case is H bonded to carbon, carbon triple bonded to nitrogen, and nitrogen having a lone pair of electrons on it. Together, that makes up the molecular structure for hydrogen cyanide. Hydrazine is another molecule where I have 4 hydrogen atoms and 2 nitrogen atoms. Nitrogen wants to form 3 bonds. Hydrogen wants to form 1. The only way to put that together is to put the 2 nitrogens bonded together with my hydrogens on the outside and a lone pair of electrons on my nitrogen. So what we typically see is that carbon forms 4 bonds and never has a lone pair. Nitrogen likes to form 3 bonds, and it usually has a lone pair of electrons on it, as is seen here on hydrogen cyanide or in hydrazine. Here's some more molecules. C2H4. Carbon wants to have 4 bonds, hydrogen wants to have 1. In this case, I put them all together, and I see that carbon to carbon I've formed a double bond, and carbon-hydrogen has single bond. So this is ethene. Okay. If I look at C2H2, again, carbon wants to have 4 bonds, hydrogen wants to have 1. Putting them all together, here I've formed a triple bond between the carbons and single bonds between the hydrogens. In the molecule ethanol, I'm going to do the same methodology. I have single bonds between carbons and carbons and hydrogens. Oxygen likes to form 2 bonds, so I form a bond between carbon and oxygen here, and that happens to be the molecular structure for ethanol. In this case, I haven't drawn in the 2 lone pair of electrons and oxygen. They're just assumed to be there, but I could draw those in also. So I have an octet around oxygen, but I haven't drawn in those lone pairs. I have an octet around carbon, an octet around carbon. Let's look at some more complicated molecules. Ethanamide. This is actually, in this case, I could arrange the atoms in different ways and still have 4 bonds to carbon, 1 bond to each hydrogen, 3 bonds to nitrogen, and 2 bonds to oxygen. But ethanamide is one way to do that. Looking at carbon, I have 4 bonds around carbon. Oxygen has 2 bonds around it. Carbon, 4 bonds. Nitrogen, 3 bonds. Again, notice that I have unpaired electrons around oxygen and a set of unpaired electrons around nitrogen. If I look at ethanoic acid, I can draw that 4 bonds to carbon, 2 bonds to oxygen, 4 bonds to carbon, 2 bonds to oxygen, 1 bond to each of these hydrogens here, and lone pairs of electrons around my oxygens. If I look at chloroethane, carbon wants 4 bonds, hydrogen wants 1, chlorine wants 1. I can arrange those together to form my octets around carbon. Notice I did not draw the lone pair of electrons along chlorine here. Sometimes that's just assumed. I wouldn't have to draw them around these oxygens either. That's just typical of a chemist. Either put them in or don't put them in. Compounds that contain elements below the second row are called hypervalent molecules. For example, anything below boron and carbon, aluminum, silicon, gallium, indium, silver, gold. Those molecules do not have to obey the octet rule, and they can form more bonds than would be predicted by the octet rule. The rationale for that is that their outermost electron shell is larger, therefore it can accommodate more than just 8 electrons. And let's look at some of those elements and molecules. Let's illustrate the nature of a hypervalent molecule by drawing the electron dot structure of SF6. We're going to use the same methodology that we did for the row 2 elements. I have sulfur, which has 6 valence electrons. I have 6 fluorines, each has 7 valence electrons for a total of 48 valence electrons. I'm going to put my least electronegative atom in the center, surrounded by all the other atoms of fluorine. I now have 1, 2, 3, 4, 5. I have 6 bonds here for a total of 12 bonding electrons. I'm going to reuse all of the remaining electrons to fulfill the octet around fluorine. So I put 6 of them around fluorine. That fulfills that octet. I have 0 electrons left. If I look at this, I do not have to do step 4 again because I've already used all my electrons. And I don't have to do step 5 because my central atom already has more than 8 valence electrons around it, so I have greater than an octet. So this represents the electronic structure of SF6. Let's continue that and let's draw the electronic dot structure for ICl3. So in this case, my iodine brings 7 electrons. My 3 chlorines each bring 7 for a total of 28 electrons. I place my least electronegative atom in the central. I surround it by my chlorine atoms. So I form 3 bonds. I have 6 bonding electrons. I then place any remaining electrons around my chlorines to fulfill its octet. In this case, I have 3 times 6, which is 18. That leaves me with 4 electrons. And this is the first case, the first example that we've looked at where I have electrons remaining. In this case, I'm just going to put them around iodine here. So I put those 4 electrons on iodine. Now I got to look at the central atom. In this case also, I have greater than an octet, so I do not have to do step 5 in this case. This is the electronic structure of ICl3. If I apply that same Lewis dot 5-step process to PCl5, IF5, and xenon F4, I get these 3 structures here. Notice in this case, I have bonding electrons and I have non-bonding electrons. In xenon, we've sort of mentioned that that is actually a noble metal, but because I'm below group 2, I can actually expand its octet, so it can be a hypervalent atom now and actually form a molecule with fluorine. Let's use the 5-step Lewis dot structure methodology for actually determining the electronic structure of some ions now. And let's start off with H3O+, which is a cation. So in this case, I take my 3 hydrogens, each has 1 valence electron. I take my oxygen, which has 6 valence electrons, and I need to subtract off 1 electron because I've made the cation. So I remove 1. So I have 9 minus 1 equals 8 valence electrons. I place my oxygen in the center. I place my 3 hydrogens around it. I have 3 bonding electrons. That gives me 2 electrons remaining. Okay, so I do not require any electrons around hydrogen, but in step 4, I'm going to replace those 2 electrons that are remaining on my oxygen here. Okay, and step 5, my octet around oxygen is fulfilled. Now I have 8 valence electrons around it. Okay, and notice here I have 3 bonds now to oxygen, and it's a cation. So that is not a neutral molecule. Oxygen can form 3 bonds, but that's going to give it a positive charge. Let's look at another cation. Let's look at NH4+. My nitrogen brings 5 electrons. Each of my hydrogens has 4. I need to subtract 1 because I have a cation, so 9 minus 1 gives me 8 valence electrons. I put my nitrogen in the middle. I surround that nitrogen with my 4 hydrogens, forming a bond to each of them. That uses 8 electrons to form those 4 bonding bonds. So I don't have any electrons remaining, and hydrogen doesn't need any, right? Because it is happy with 2 electrons in its outermost shell. I don't have any electrons remaining because I've already used them all up. And my octet around nitrogen is complete, so I don't have to do step 5. Let's now use our 5-step Lewis dot structure methodology for determining the electronic structure for CH2O2-, which is an anion. So my carbon has 4 electrons. My 1 hydrogen has 1. I have 2 oxygen with 6 electrons, and it's an anion, so I'm going to add an electron to that. So I have a total of 18 valence electrons. I organize my atoms around the central least electronegative carbon atom, so I have 2 bonds to oxygen and 1 bond to hydrogen for 6 bonding electrons. I'm going to use any remaining electrons I have to put them around oxygen to fulfill its octet. So I use 12 electrons around oxygen. I have 0 electrons left, so I do not require any electrons around the central atom. On step 5, because oxygen here has extra electrons, I'm going to use that to actually form a double bond to carbon here. So if I form one double bond here, notice I have 1, 2, 3, 4. I have 4 double bonds to oxygen. That's stable. I have 2 bonds here to oxygen. That's stable. And I have only 1 bond to oxygen here. That's why this is an unstable structure. It would like to form another bond with oxygen to form a structure. So this gives me the electronic structure of CHO2-. It also tells me that this is a reactive structure. It wants to form a bond with oxygen here, so oxygen gets a second bond here.